Hi everyone and welcome to a new video. We continue with our transistor circuits. In this case we will discuss the BJT amplifier and this will be our example number 1. We have so far seen the DC analysis of the BJT, the transistor type. In this case we will also see that in the amplifier configuration. So we will use still the DC analysis, and on top of that we will look at the AC analysis and also the time response. In this case we will look at the NPN transistor type, and this will be also called a common emitter amplifier. Of course we will work out everything in the calculation step by step and also verify our calculations in SPICE simulations. So let's look at an example. We have this circuit given. The circuit here has now an AC source, this one yellow, VI, and on top of that in series we have the VBB, which is the DC biasing for the input. The transistor is shown here, which is the NPN BJT transistor. And we also have the VCC, which is our DC voltage source. We have two resistors, the collector resistor RC and the base resistor RB. And we measure here at this node, which is the collector, the output, which is VO. You see three arrows here, IC, IB and IE. Those are the total values of the AC and the DC quantities together. That's why we have a capital letter and a small letter for a subscript. So we have the IC, IB and IE in the same configuration. Also for the collector emitter and also the base emitter voltages. Okay, we have the following data. VBB, which is 3 volts, VCC is 20, and we have the RB is 100 kilo ohms, and we have RC is 4 kilo ohms. The VBE again is the base emitter junction, is considered to be 0.7 volts. The beta in this case for the transistor is 100. So we like to calculate the following, which is the DC operating point values, which is the base current, the collector current, the emitter current, all of them in the DC, and also the collector emitter voltage, which is the DC quantity. And then in question B, we like to calculate the voltage gain, which is the V out over V in. Okay, let's look at our solutions. We assume before we start that everything is operating in the linear region for the BJT. That means the collector current is equal to the beta times the base current, which is shown here. So there is a linear relationship between the collector and the base current. So let's look at the solutions. Okay, the question A, we will start with the Kirchhoff's voltage law at the input loop, which is this loop. Now for the DC analysis, we consider the AC sources disabled, so we can short this VI source. Then we can set the following. We can say the VBB is equal to the IB times the RB, which is then the DC quantity of the base current. That's why we have a capital letter B as a subscript, plus the VBE. Now, we can now calculate the IB, which is the DC base current, using this formula. We know everything here. We say down 3 minus 0.7 over 100 kilo ohms, you'll get 23 microamps. Okay. Then we have the following. Since we know the base current, we can calculate the collector current using this formula, and we have 100 times the base current, we have 2.3 milliamps. In a similar case, we know that the emitter current is the summation of the collector and the base current. That's shown here, so beta plus 1 times the base current is the emitter current, and you will get approximately exactly here 2.323 milliamps. So we have now the 3 DC currents in the circuit. Next one is the VCE, which is the collector emitter voltages. That's then done in the output loop using Kirchhoff's voltage law. So the VCC is equal to RC times IC plus that VCE. So VCE is then VCC minus RC times IC. Now we know here everything. We can just substitute the values here. We can say VCE is then 20 minus 4000 times the 2.3 milliamps for the IC. That will give us 10.8 volts. Okay, we have now the quantities for question A. Now moving into question B, we start with the small signal model. And this model here is the small signal model for the transistor only, this part in red dashed line. So in this box, we see the R pi, which is a dynamic resistance of that BJT. And we see also a dependent source, which is called the beta times IB, which is the AC collector current. So this current here is dependent on the base current, which will flow through the R pi. We will calculate shortly what the R pi is. Also use this in this circuit. You can also use it using the GM times V pi, which is then this voltage times the GM. And again, there is a formula for that. So it depends on which you prefer. You can use the beta times IB or the GM times the V pi for this dependent source. You see the base, the collector, and the emitter nodes for this. So this dashed red box is only that transistor. And outside we see the RB and also the AC sources. So everything in DC domain is disabled. That's why you also see this RC from the collector node to the DC voltage or VCC ground, because this node is now grounded in AC domain. That's what you see here. So everything is grounded here. Now we measure also the voltage between this node, collector, and ground, and that is also the same here. Okay, we will use this small signal model. This is also called the hybrid pi model in the very simple configuration. Okay, what do we see? We need a VO over VI expression, so let's then determine each of them separately. VI, this voltage, is equal to the summation of these two resistors, RB and R pi, times the current which is flowing here. It is actually this loop, which is then given by Ohm's law. We can also say for the VO, which is output voltage, is this voltage here across resistor RC, but that is the reverse of this IC. That's why we have a minus sign here, because the current here will flow from this the bottom node to the top node, while we measure from the top node to the bottom, to ground. That means we have a sign inversion, which is this one. But we know IC is also equal to minus IC is equal to beta times IB, which is then given here. Now, if we now take this together and then make the ratio of VO over VI, we have this. You can see that we now can delete out or divide out the IBs. Then we have the following expression, which is then minus beta times RC over RB plus R pi. And this is now the expression for the voltage gain. Then we can use that for the actual numerical value of the voltage gain. We also see that the minus sign here, so there is a sign inversion. But if you want to use that GM, you can calculate that or express that using this expression, which is then beta, which is unitless, is equal to R pi, which has the units of ohms, times the GM, which is 1 over the ohms or Siemens. So this product will give you the current gain of the transistor. So we have also this, so you can substitute here R pi times GM and then divide by the R pi, the numerator and denominator. You will get this expression. So it doesn't matter which one you prefer, you will get the exact same result. So using this, we continue. Now also discuss what the R pi is. R pi is a dynamic resistance. It depends on the DC value of your base current using this formula. The VT here is called the terminal voltage, and it depends on the temperature and also other factors. So in this case, it is most of the time taking as 26 millivolts for approximately 300 kelvins. That is approximately 26 degrees. Now, if we use that, most of the time we can just use that, assuming the temperature is in that region, divided by the DC base current we have calculated, 23 microamps, and then we get 1130 ohms, so 1.13 kilo ohms for our R pi. Now we have everything to calculate the gain. We can say AV, the voltage gain amplification for the voltage, is VO over VI, which is this, or that doesn't matter. This one is then minus 100 times 4000 over 10 to the power 5 plus 1130. That will give us minus 3.955, almost minus 4. Okay, that's the gain. And we also have the DC values in question A. Okay, collect them together. Let's see also what we have in the simulations. First, we start with DC analysis and see that it is indeed correct or not. So we will check that. This is the DC circuit. You see the V in, now, and also on top of that the VBB, which is actually this circuit. We see the current arrow here to measure the IB. You see it is 23.34 microamps, so a little bit larger than what we have calculated, just a small error. That is really due to that extra modeling in the transistor, which we do not account in our example. So that is normal that you have a small difference. Of course, this will be multiplied by 100, so you will get a little bit larger current for the collector. That's also shown here. And on top of that, of course, you will get a little bit larger emitter current, so everything is also shown here. Since the emitter current and also the collector current are a little bit larger, the voltage drop across RC is larger, so you will get less current here or voltage here across the VCE. This voltage here, which is now 10.66 approximately, is this voltage between this and ground, which is also the same as the VCE. We had 10.8, so it is a little bit smaller than in the calculation. In the calculation, it's a little bit larger than in the simulator because the current is larger. So that is what we see here. But it is very close to what we have calculated, so we can say this is perfectly fine. Okay, that's for the DC analysis. Let's move on now to transient response, which is then the actual gain. This is the complete plot. What you see here is very interesting. The top one is the base current. This is the collector current, the pink one. The green one is the emitter current. The blue one is the input voltage waveform, and the output voltage is the red one. Input is 20 millivolts peak sine wave, and it has a frequency of, in this case, 100 Hertz. So it's peak 40 millivolts. Now you see here for the base current, let me start with that one. Base current has a level of average value of 23.34 microamps, which is what we have seen in the simulator, and that's also close to what we have calculated. As you see that 23 microamps. So this value is our operating current, and on top of that we have a swing up and down. That is the AC quantity. You see it also for the collector. This is the DC value, and this is the variation around that DC value for the current, also for the emitter, the same thing. Now we have a level for the Vin, which is starting at 0, so that is symmetric, around 0. And we see here that is 10.66, so that's actually what we also saw in the simulator. And we also see that it is also varying sinusoidally, but it is inverted, so there is a phase shift of 180 degrees. Now what we also see in addition is that the peak value for 40 millivolts for the input will result in 158 millivolts at the output. So we see the minimum, the maximum and the minimum values for the output voltage. Now that will then give us following, because the gain, voltage gain, is peak output voltage divided by the peak input voltage, considering everything is linear, no distortion. Now we can see the following then, 0.158 for the output, peak, divided by 0.04, that is the 40 millivolts peak for the input, and you will get minus 3.95, which is very close to what we have calculated here. So there's really small errors again due to that extra modeling in the simulator itself. So we can say this is perfectly fine, and we verified now our calculations also in the simulator for this very simple circuit. One of the things here to consider is that the effect of the beta is enormous here when this beta value will changes. If this beta is changing from, for example, from 100 to 200, a lot of things will change, and there is no compensation or any feedback mechanism to set this gain to a very constant value. So this is not a very practical circuit for our amplification, but it is a very good starting point to understand the material. In the next example, example number 2, I will discuss another BJT amplifier having an emitter resistance where you see that actual bias stable operation. Alright guys, this is for our first example about the BJT amplifier, considering the very simple circuit and also the DC and AC analysis separately. If you have any questions about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.